All right, let's take a look at this problem. This is chapter 6, problem 39. We're going to start by drawing the free body diagram for this problem. So we're going to use the beam as the object of interest, and we're drawing the tension on rope number 2 at 30 degrees from the vertical, and we have tension on rope 1 at 20 degrees from the vertical. The other force acting on the system is the force of gravity, Fg, and we know that the object is being supported by the cables, so that means that the object is in equilibrium, and in equilibrium the sum of the forces should be 0 because the acceleration is 0. So in particular we can write that specifically we can write that the sum of the forces in the x direction equals 0, the sum of the forces in the y direction is 0. So we're going to use the x and the y axis in the usual way. In the x direction, we need to find the components of the tension 2 and tension 1. So let's start with tension 2 in the x direction. What we're going to do is add the x components of all the forces acting on the system, but the force of gravity clearly doesn't have an x component, so we're just going to be finding the x component of T2 and the x component of T1. So the sum of T2x and T1x is equal to 0. The x component of T2 is that vector that I'm drawing over there. Notice that is the opposite of the 30-degree angle. So therefore, opposite goes with sign. So T2x is T2 sine of 30 degrees. And it is positive because it's pointing to the right. That's the positive x-axis. Now the T1 force, the tension in rope number 1, is at 20 degrees with the vertical and pointing in the second quadrant. So the x component is actually going to be negative. As you can see there, T1x points in the negative x direction. So T1x is going to be, well, remember that the reason why this is going to be negative is because the component vector T1x is equal to a number multiplied by I hat. I hat is defined as a unitary vector in the positive x direction. Since T1x is pointing in the negative x direction, the number T1x is a negative number. So the x component of T1 needs to be entered as a negative number. Its magnitude is T1 times the sine of 20 degrees. And the sum of those two is equal to 0. So putting that, moving the T1 sine 20 to the other side, gives us this equation: T2 sine 30 degrees equals T1 sine of 20 degrees. So out of this equation, we're looking for the values of T1 and T2, but clearly at this point we can't really figure out how many newtons is each one because we don't know the value of either one of them. So that means we're going to have to use another equation. The other equation is the sum of the forces in the y direction. We just used the sum of the forces in the x direction. Now we're going to use sum of the forces in the y direction. Since this is an equilibrium problem, no motion, then the acceleration is 0, and the sum of the forces in the y should be equal to 0. What are the y components of those vectors? T2y points like that red arrow that I drew there, T1y also, and we have the force of gravity pointing straight down in the y direction. So T2y is going to be the adjacent of 30 degrees. It is a positive value. So it's going to be T2 times the cosine of 30 degrees. Again, look at the picture. T2y is the adjacent of 30 degrees. So it goes with cosine. For T1y, we have that T1y is the adjacent of 20 degrees. So T1 cosine of 20 degrees will be that component. So now we add all the y component of all the vectors acting here. T2y and T1y are positive. Figure they are T2 cosine 30 and T1 cosine 20. And the weight of the object is negative. The y component is negative because it's pointing down. So those three add up to 0. So T2 cosine 30 plus T1 cosine 20 equals the mass, which is 1,000 kilograms multiplied by 9.8, the acceleration due to gravity, and that gives us 9,800 newtons. So we have so far T2 cosine 30 degrees plus T1 cosine 20 degrees equals 9800. So we got these two equations inside the rectangles. T2 sine 30 degrees equals T1 sine 20 degrees, and we have T2 cosine 30 plus T1 cosine 20 equals 9800. So we basically have a system of two equations with two unknowns. So now it's the time to pull out your calculator and replace the angles and find the sines and the cosines that we need. So for the first equation, T2 sine 30 degrees, we're going to write it as T2 times sine of 30, which is 0.5. So T2 times 0.5 equals T1 sine of 20 degrees, which is the number in your screen, 0.342. And then the other equation, the other inside the rectangle, is T2 cosine of 30. So cosine of 30 degrees is 0.866, then times T2, plus cosine of 20 degrees, which is 0.939, multiplied by T1 equals 9800. Those are two equations, two unknowns. So you learn how to do this in your algebra class. So what we're going to do is solve for T2 in the first equation and then replace that value into the second equation. So from the first equation, T2 will be 0.342 divided by 0.5 times T1. Putting in the numbers in the calculator, you get 0.684 times T1 is equal to T2. And now we're going to substitute that value into equation number 2. Right there. So 0.866 times 0.684 times T1 plus 0.939 T1 equals 9800. That multiplication there gives us 0.592 T1 plus 0.939 T1 equals 9800. So factor out the T1, add the numbers, and you get T1 times 1.53 equals 9800, which gives you T1 equals 6399.6, which I'm going to round to 6400 newtons. So knowing the value of T1, we can use the equation inside the rectangle, this rectangle right here, and we're going to replace T1 to get T2. So T2 is going to be 0.684 times 6400. Final answer is 4,377, which I'm going to round to 4,380 newtons. So those are the two answers for the tension. All right, let's do another one here from your textbook also. This is chapter 5, I believe, problem number 9. So this problem is showing us the forces, the free body diagram for an object that is a 2 kilogram object, and we're looking for the values of the acceleration in the x direction and the acceleration in the y direction. So notice that the x and the y axis have been tilted, so you gotta be careful with that. Follow or use those axes and to express the components of all the vectors. So mass is 2 kilograms, that was given, and we're looking for acceleration in the x and acceleration in the y. So free body diagram provided, notice the axis. I'm going to add to the free body diagram that the angle that the 3 Newton makes with the y-axis is going to be, how much is that going to be? So the angle given there was 20 degrees between the x-axis and a horizontal line. So for the right angle triangle formed by the 1 Newton direction, or by the x-axis and the 3 Newton force and the horizontal, we know that the upper angle is going to be 70 degrees, and since the angle between the x and the y-axis is 90, it must be that the angle between the 3 Newton vector and the y-axis is 20 degrees. So let me clean that up, and we know that that angle is 20 degrees. Alright, so we're ready to start by finding the sum of the forces in the x direction, which would allow us to find what's the acceleration in the x direction. Then we'll do the same for the y components. So sum of the forces in the x direction equals mass times acceleration in the x. So in the x direction we have a 5 Newton force positive. We have a 1 Newton force pointing to the left or towards the negative x-axis, so that counts as an x component that is negative for that vector. And we have the the x component of the 3 Newton force, which, as you can see in the picture, is the x component will be the side that is opposite to 20 degrees, and it is pointing towards the left. The x component is pointing towards the negative x-axis. Therefore, it counts as a negative component, minus 3 newtons times the sine of 20 degrees. The the force that points straight on the y-axis, the 2.82 newtons, that one doesn't have an x component, so that one is not going to be included. And the sum of the x components is equal to the mass, 2 kilograms, times the acceleration in the x direction. So 5 minus 1 is 4, and 3 newtons times the sine of 20 degrees is 1.026. And if we divide that by 2 kilograms, then the right hand side should be the x component of the acceleration. So plugging in the calculator, you get that the acceleration is positive and it is equal to 1.486 meters per second squared. So we know that this object is accelerating in the positive x direction. So we got half of the answers that we needed. Now we need to move on to the y components. So sum of the forces in the y direction divided by the mass should be the y acceleration. So forces in the y direction, clearly the 2.82 newtons is in the y direction. We have the component of the 3 Newton force pointing in the negative y, so that will be 3 times the cosine of 20, and we're going to divide by the 2 kilogram mass to get the acceleration. Turns out that when you put those numbers in your calculator, you're going to get 0 or something very close to 0, 0.0000 something. So basically the acceleration in the y direction is 0. So notice that this problem actually has, or you can think of a physical situation that would have a free body diagram just like this one. What is that physical situation? An incline, right? 20-degree angle for the incline, and you have an object, say a block, and you're pulling on that block along the incline with 5 newtons of force. The block has friction with the incline, so that's the 1 Newton force. The block has weight, of course, that's the 3 Newton vector going down, and there is a normal force with the incline, which is 2.82. Now the acceleration that we got for the x direction is 1.486 positive. So that means that the 5 Newton force, which probably is applied in a real life situation, will be applied with a string. That force is bigger than the component of the weight and the friction, and it makes the block accelerate up the incline. That's what we're getting. Up the incline is the acceleration because it is positive. And as in a real life situation with this block on an incline, we also got in this problem that the acceleration in the y is 0, which is exactly what you expect because the block moves on the inclined surface. The block doesn't take off from the surface, the block doesn't dig into the surface. So remaining on the surface means that the acceleration of the object perpendicular to the surface is 0. And that's what we got. We got AY equals 0. All right?